Welcome back to the lectures on GPU architectures and programming. So, in the last lecture we have just started the discussion on kernel fusion, one of the possible optimizations in GPU programs, and we have classified the different kinds of fusion optimizations that are possible. Just to recall, they were inner thread fusion, inner block fusion, and inter block fusion. So, let's get into the detail of what is inner thread fusion. So, essentially when we speak about inner thread fusion, so suppose I have kernel 1 executing on some data segments and computing some output, which is to be then again passed to kernel 2. So, consider that there is a dependency graph where you have an input buffer. So, this data stream would be operated by kernel 1, it would be returned to some output buffer, and then it would be again read by kernel 2, and then it would be output again to some output buffer. All we are doing is essentially just fuse this part, create one kernel, and let each of the threads perform the operations of kernel K1 followed by the operations of kernel K2, right. So, essentially we are allocating the job per thread from kernel 1 followed by kernel 2 to a single kernel where each thread performs the operations of kernel 1 followed by kernel 2. So, if you remember the example we took earlier, let me just go back to the task graph here. This was the task graph of kernels and we fused all of them. So, this is this was my version of the fused kernel. As you can see that the final fusion is at the thread level. We compute the global thread ID, we examine whether it is inside the valid data size, then I just perform per thread the sequence of operations which were to be performed by each of the 3 kernels individually. I have just written down those operations in a sequence, right, without violating the sequence that was already provided by the partial order that was enforced by the original kernel DAG, right. So, this is in a nutshell the idea of kernel fusion when we do inner thread fusion. So, you just write a per thread activity which is a sequence of the 2 kernel codes, right. Now, the issue is how do I decide on the threads per block and the number of thread blocks when designing a inner thread fused kernel. So, you are essentially combining the computation of the 2 kernels at the single thread level. It is suitable for both dependent and independent kernels. So, dependent kernel would mean that the first kernel's output is the input for the second kernel as we saw in the task graph. So, every edge in the graph is like a dependency edge, and so it is suitable in that case, and it is also suitable for independent kernels, but there is a constraint that the data space size has to be same, so that we can use the same data space size to define identical thread blocks for the fused kernel, right. So, consider that STHI represents the size of threads in a thread block. So, that is the thread block size, and SBKI represents the size of blocks in the kernel, or essentially I would say the number of blocks in the kernel, right. So, this is the size of let us just rewrite this, represents the size of thread block. So, this is the number of threads per block, and SBKI represents the number of blocks in kernel I, right. So, when I fuse them, I have to set the number of blocks and number of threads per block, right. I need to identify what is my number of blocks, and I need to identify what is my number of threads per block. So, when I fuse the two kernels to create a single kernel, I choose STH, which is the size of thread block as the max of the individual thread block sizes, and I choose the number of blocks as the maximum of the number of blocks in the individual kernels. Okay. Now, why is this important? Because of course, when I am fusing two different kernels, they may be considering different data space sizes. I mean, they may be considering different ways in which the threads are arranged in the data space, although maybe the data space size is same. So, when I write the fused kernel, I have to choose STH, the thread block size, and I have to choose SBK, which is the number of blocks, right. So, in that way, for when I am doing an inner thread fusion, I set these parameters by doing a max in each case, and the issue is this is not a good optimization in case the kernels do not have same thread or block. I mean the arrangement of threads and threads per block space is very different. So, if the kernels are not having the same threads per block in the data space, then it's not a suitable optimization. Primarily, the reason is that it would result in an unbalanced issue of workload. I mean, the kernels different thread blocks will have different amount of work to do, and that would be issue with respect to exploiting the parallelism of the GPU in general, right. So, we will actually prefer this kind of an optimization if the number of blocks and number of threads per block, primarily the number of threads per block, are kind of similar across the different kernels. Let's move to an example and try and figure out why this is really so. So, consider this situation. So, I am doing an inner thread fusion. So, this is the original unfused version, and this is the fused version. Now, this is an example where we are showing that the number of the STH1 and is STH1, the number of threads per block, that's 2, and SBK1 number of blocks is 6, and we are just considering a very ideal situation where everything is same for K1, K2, and I am just fusing them to create the fused kernel KF with STH and SBK as the number of threads per block and the number of blocks, right. So, it is just a max of STH1, STH2 and max of SBK1, SBK2. Since they are all same, so I get the same values here. So, when I am going to fuse as long as but the important thing here is these kernels, if I am considering K1 and K2, they are independent, right, but then K3 depends on K1 and K2, right. So, it is not that all the kernels are independent, they have some ordering as is enforced by the DAG structure here, right. So, as long as we are fusing dependent kernels with the same data space size and threads per block size, the code is very simple. So, let us say these are the unfused kernels, and we are just trying to provide. So, as you can see that we are just providing a structure of the kernel code. Let us say K1 structure is like this, that you just compute the global thread ID again. So, this is not the valid kernel code, we are just providing a structure of K1, structure of K2 here. So, for K1 you compute the global thread ID, do the operation. For K2 you compute the global thread ID and do the operation. When you fuse them, you will have some local variables to hold intermediate results. So, for that you should have some more variables C and D here. Compute the global thread ID as long as it is inside the data space size. You compute the first operation of K1, store it in local variable C, compute the operation of K2, store it in local variable D, use C and D to compute the final output, right. So, yeah. So, you use C and D to compute the final output, which would be square root of the first kernel's output multiplied by the square root of the first kernel's output multiplied by the second kernel's output, that is the final value, which is the final fused value, right. So, this was a very easy piece of code, simply because the threads per block and the number of blocks are all same across the kernels. So, things look very simple here, right. So, now consider this simple thing as in a situation where you have the same data space sizes, but now we have some different data space size, but same threads per block size. So, again I am just recapitulating here. So, this is the inner thread fusion example, and this is the very simple situation. This picture is just showing. So, unlike this program which was the total fused kernel, this picture is just showing how the K1 and K2's fusion will look like, right, very similar, just missing the code for K3 here, but this is very simple, the fusion is quite simple for K1 and K2. So, this is a difference with this is here I also have K3 in the final output. Here I am just showing the example of fusing K1 and K2 here, the two simple operations are done, right. But now consider the situation where where you have a bit difference in the data space size. So, suppose the situation is that you have same number of threads per block, but you have a difference in the number of blocks, right. So, that is what the picture is trying to convey here, right. So, K1 is operating like this. So, for K1 the block structure is did, you have 2 threads per block, in total you have 6 blocks, but K2 is operating on a larger size D here, right. So, here for K2 you have this 4 threads 4 blocks, and but the threads per block is same. Now, how do I fuse them? Because I am going to produce the outputs, right, C and E. So, as you can see, we have now taken an example where the data space size is varying, but that since I do not have K3 in this example, I just have K1 and K2, I do not have a problem, because K1 and K2 are independent kernels, right. So, as long as they are independent kernels, I can always fuse them together even if the data space size is different, right, as is the case here. The data space size is different here, but with in this case example we have the same structure of threads per block. That is also important in this case, because since the thread per block is same, it does not change even in the fused kernel. If I follow the formula, it is equal to whatever was for the K1 and whatever was K2 is same, but since I am doing a max over block size, the number of blocks is now same as the kernel with the larger block size, the number of blocks, right. So, when I am fusing the kernels K1 and K2 which are independent, for the output kernel the Kf, I have the larger number of blocks, but the thread per blocks remains same as the two originals, right. So, I hope the point is clear. When we were fusing all the 3 kernels together, we had the requirement that data space size has to be same, but now since K1 and K2 are independent kernels, I do not have that requirement, because K3 is not there to work on the final output, and for since they are independent, they can actually have different data space sizes, which is the situation here. And when I am fusing them, so it's again quite simple. So, I is less than n, then I have the sequence of values, so the program automatically takes care of the situation that for that I am, since I have considered the larger number of blocks in my definition of Kf. So, automatically the fused kernel will launch the number of threads similar to the whatever is required for processing. It's going to launch the number of threads which is similar to the requirements of K2, which had the increased number of blocks, and so there will be enough threads to process the data buffers in D, and apart from some of the threads which are lying in these blocks, all the other threads will also be processing the data buffers from A and B, as was the requirement for K1, right. So, I hope this is clear. Since the two kernels are independent, the fused kernel code is also very simple in this case, right. Now, coming to the limitations of inner thread fusion. So, if I am fusing independent kernels with both different data size and threads per block size. Now, it may be unsuitable in this case. Again, I will just come back here. Here we had the number of blocks differing across independent kernels, but the number of threads per block was same, right. That was a good thing, and that led to a very simple code, right. That just led to a very simple code. So, this was my code for the inner thread fused kernel. Sorry, we didn't talk about, maybe we skipped this earlier. So, this is my code of the inner thread fused kernel, considering a difference in the overall data size due to the difference in the number of thread blocks, but both of them having the same threads per block size. So, as you can see that you compute the global thread ID, and then you have to figure out whether the global thread ID would be inside the range of both the kernels, or is it outside the range of kernel 1, but inside the range of kernel 2. If it is inside the range of both the kernels, which is N1 here, then I should actually compute whatever is the operations for both K1 and K2, right. So, then I am inside thread ID I, which is lying in this common region, and otherwise I will go to the other region where I have to only execute the code for kernel 2, right. So, again we will just recall that these are independent kernels with unbalanced number of blocks, but same amount of but same amount of threads per block, right. So, the different data size is there due to the unbalanced number of blocks, right. Now, consider the situation where I have a different number of blocks and also different number of threads per block. Now, that may be a bad thing in even for independent kernels, because consider K1 and K2 with this arrangement. So, 2 threads per block and 6 blocks, and 4 threads per block and 4 blocks. So, overall in KF I am going to have 6 blocks, and in 6 blocks some of the blocks I have full fusion, right. So, I have 4 threads, in some of the blocks I have only 2 threads, because if we notice the first block I should have 4 threads. 2 of the threads will execute code for K1 as well as K2, 2 of the threads will execute only the code for K2, right. And the same pattern will continue for the other 3 blocks also here, right. I hope this is clear that why this may not be a good solution in this case. First of all, the classification of this case is unlike the earlier case where I had same number of threads per block, but varying blocks. Here I have varying threads per block as well as varying number of blocks, right. Now, due to that, when I am fusing, due to the issue of varying number of blocks, I will have some blocks where there is no activity of kernel 1. For example, these 2 blocks, no activity of kernel 2, which has less number of blocks, right. So, such blocks are these 2 blocks. For the other blocks, I have unbalanced execution. For example, all these 4 blocks, as you can see, there are 2 threads. So, each block has 4 threads, which is the max of the threads per block of K1 and K2. And inside these 4 threads, there are 2 threads which are executing code for both K1 and K2, and 2 threads which are executing the code only for K2. So, this leads to a lot of unbalanced execution, which may not be good. Now, this leads us to another possible way of fusion. I hope by now this idea of inner thread fusion is clear to you, and this would actually lead us to the other possible ways in which we can fuse, and they are inner block fusion and inter block fusion. So, before going into them, let us again summarize the good and bad things of inner thread fusion. So, when you do a thread level fusion of 2 different kernels, if they are independent kernels with both differences in both thread number of blocks as well as threads per block size, it may lead to a bad a bad situation, complete unbalanced workloads, and that may not be suitable. In some cases it's okay. For example, the data size is different, but because the number of blocks are different, but the threads per block are same. So in that case, the code is doesn't have too much overhead, and there is significant amount of balance in execution of the majority of the blocks. This was the picture for that. And when I consider the total fusion of the blocks, our demand was that okay, there should be absolutely same data space size and thread block size. And we now coming back to this part, it would make sense, right? So this is the situation where I am fusing independent kernels. As long as I consider only K1 and K2, they are just independent kernels. If we go back to the earlier example, which was this, so here I was using K1, K2 and K3. So there was also dependency, which means I can start the code for K3 only when K1 and K2 both finishes, right? Now the issue is, as long as I have identical number of threads per block and identical number of blocks, fusion of dependent kernels is good, is simple in this case while considering inner thread fusion. But now, as we have understood now what is the implication of differences among even independent kernels. So this was my picture of independent kernels getting fused, where they have differences in number of blocks as well as threads per block. So we understood what is the issue here. Now one can easily visualize that how the issue becomes even difficult when you are trying to use this concept of fusion in the case where you have dependencies among kernels and there is no balance in terms of equality of threads per block and the number of blocks while executing dependent kernels if you are going for fusion. So as you can understand that if I am trying to fuse this with identical number of threads per block and number of blocks, things are very simple. My checks are very simple. Just check on the global thread ID and execute all the operations in sequence. If there is difference in the number of threads per block, if there is difference in number of blocks in some of the kernels, it would be really difficult here. I need to do more fine-grained control by introducing more number of if statements, and that would be further complicated if I have also variation in threads per block setting also. That is why in case of dependent kernels it's even more complicated, and we had an idea of that by even looking at the situation for independent kernels, because as we saw, as long as it was independent kernel with with everything same, that is I have same number of blocks and same number of threads per block, right? That is the same data space size and same threads per block. Then the code was so simple, just a check on whether I am inside the data space. The moment we introduced one difference, that is okay, let the threads per block remain same, but let there be more number of blocks so that there is a difference in the data size. That introduced one if else statement to check whether I am inside the block whether I am inside the common blocks or I am in the blocks only relevant to K2. So the more I am going into this mess of the differences in threads per block and as well as differences in number of blocks, it's only going to introduce more and more of conditionals even for dependent kernels, and the overall program will get much more complicated with more primitives required in case of dependent this is already sufficiently complex in case of independent kernels, and that would require additional primitives if I am going to use this concept in case of dependent kernels where I also have variations in threads per block as well as block size, right? So from this the point to take home would be that when I am trying to fuse independent kernels, we should take care that at least there is similarity of threads per block size, even if there are differences in block size. But if we have differences in blocks, number of blocks as well as threads per block, it's already absence of there may be significant absence of balance in the workloads in the fused version, and If we bring in the added complication of dependency among kernels, it would require more preventives, which would complicate things even further. So, we understand now when inner thread fusion is absolutely fine, as long as there is full identical arrangement of the data space across the different kernels. And even if that is not the case, if at least threads per block remains same, still things are okay for the case of independent kernels. And when I have variation in threads STH as well as SBK, then it's very difficult to achieve workload balance among threads for inner thread fusion, even for independent kernels. And it's better in those cases to look for other optimizations in respect to fusion, like inner block fusion or inter block fusion. So, with this we will be ending this lecture, and in the next lecture we will be looking into the more details of inner block fusion, and that would be all for this lecture. Thank you.